Okay, so this is our last video on polar coordinates, and what we're going to do now is we're going to define the limits of integration in polar coordinates for something that might be something like this. So let's suppose that this is some region D that is not centered at the origin. So it's a circular region not centered at the origin. It actually has center at AB. So basically we know from the equation of the circle that we can write this as x minus a squared plus x minus b squared. Sorry, y minus b squared is equal, or in this case, because we're treating a region, so the region inside the circle, including the circumference itself, is going to be equal to the radius of the circle, which is a fixed radius, it's constant. And the question is, how do we find the limits for both theta and r in this case? Because remember that what is r doing here? R is basically tracing a trajectory on that circumference from the origin here, so r is just like a vector. And then it is tracing the circumference like this. So what is going to be the minimum value of r? What's going to be the maximum? They're not going to be constant because now r is going to depend on that rotation. So this is a little bit more complicated, but essentially the way in which you derive the limits for theta, first of all, for a circle that is not centered in the origin is you look at which quadrants does it cover. So if we have our 4 quadrants here and we have, say, a circular area here, then this circular area is covering 2 quadrants, so the first 2, which means that theta is going to have the following limits, 0 to pi, and it is as simple as that. If it is covering only all 4 quadrants like that, but it's not centered at the origin, then it is covering all 4 quadrants, so that means that theta is going to go from 0 to 2 pi. And then in this particular case, it is only covering the first quadrant, so that means that this is going to go from 0 to pi on 2. So that's easy enough. Now for r it's a bit more complicated, and in order to derive the limits for r, we need to solve this equation for the circle. So the first thing we're going to do is expand this side, so we're going to get x squared minus 2ax plus a squared plus y squared minus 2by plus b squared. And just for the sake of argument, let's set this equal to r squared, because remember it's not gonna change much in terms of what we can or can't do, because in the end when we get r from this equation, we're going to be solving for 2 values. So what we're going to do is we're going to group these x and y, and remember the definition, x squared plus y squared equals to r squared. So in this case we can write r squared, and what we're going to do with x and y is we're going to replace them by the parameterization. So we know x equals to r cos theta and y is equal to r sine theta. So this is going to become r minus 2 minus a r cos theta minus 2b r sine theta. And then these 2 terms, let's move them to the other side. So that's going to be r squared minus a squared plus b squared. So this side is just going to be a bunch of constants. So what do we have here now? Well, we have a really interesting thing, because we can factorize r out of the picture. So we're going to have the following expression, r minus 2a cos theta minus 2b sine theta equals to r squared minus a squared plus b squared. That's what we're going to have. Now the really interesting thing about this is that this basically reduces to a problem of finding the roots. This is a quadratic equation on r, where everything else except for theta is treated as a constant. So theta, the reason we have theta in here, even though it's another variable, is because remember that when we perform the integration in polar coordinates, we always start with the dr element. So obviously if our limits depend on theta, that means that first we integrate with respect to this, get an expression in terms of theta, and then integrate with respect to theta using the constant limit. So in the end we get a numerical value as we'd expect. So that it's completely fine to have these kind of things in the limits of r, because we're integrating with respect to r first. Now, obviously for this quadratic expression, we're going to get 2 roots for the expression. Those 2 roots are going to be the limits of integration in r. So the minimum is going to go here, and the maximum root is going to go here. So that's fairly straightforward. The problem is that obviously finding the roots for an expression like this is fairly complicated. The only simple case is when this side is equal to 0, in that case we can find the roots, and r would go from 0 to the point at which r is equal to the sum of these two. So that would be a fairly simple example. But in the general case where we have this thing where it is not, this side is not equal to 0, then performing this kind of integration substitution is going to be fairly complicated, because you can imagine that we're going to get a massive expression involving cosine and sine theta. So let's consider a simple example just to get an idea of how this works. So let's suppose we have the following problem. We have a circle. We have a circle of radius 2. And we have 4 in here. Y, x. So this is going to be a region of integration. And then this is basically a circle of radius 2. Right? And now the idea is we're going to integrate the following function. So this is going to be square root of x squared plus y squared on the a. So the way we're going to go about this is basically, first of all, we're going to replace these limits with polar coordinates. So first of all, establish the limits of integration in polar coordinates. So for theta, we're going to have this circle covers the first and the second quadrant. So that's going to go from 0 to pi. And now r is going to go from where? So to find the limits, we're going to apply the circle formula. So let's write the equation of the circle of this region. So that's going to be x minus, so this is 0 here, so that's just going to be x squared plus y minus 2 squared. Let's have it equal to 2. So that's the radius of the circle. And actually it should be radius squared, so that's going to be 2 squared. And now we're going to have the following. So let's expand this out. That's x squared plus y squared minus 4y plus 4 equals to 4. So these two 4's cancel out. Now let's replace this by r squared, and let's replace this by minus 4 times r sine theta. This is going to be equal to 0, and we can factorize this in the following way. So we're going to have r times r minus 4 sine theta. So given this expression, because we have 0 on this side, we have two simple roots. So the first one is going to be, so the roots of r in this quadratic equation are going to be 0 and 4 sine theta. So those are the two values that are going to satisfy this equation. So that means that we start from here, from 0, and then we go all the way to 4 sine theta. So that's going to be the limit on r. So now that we have that, we can actually rewrite our integral as follows. We can rewrite the integral as follows. So let's have 0 to pi, from 0 to 4 sine theta. Now we're going to have r squared, so x squared plus y squared, that becomes r squared. Square root of that is r. And now the area element is going to be r d theta. So we're going to get the following. We're going to get 0, 4 sine theta, r squared dr d theta. This is going to be equal to, let's take out the 3. So 1 over 3, 0 pi of r cubed, 4 sine theta, 0 d theta. And now this is going to be from 0 to pi, so 1 over 3 of 0 to pi. And now, actually, let me evaluate this first. So when we put 0 into here, nothing happens, that vanishes. But when we have 4 sine theta, we are going to have 4 to the power of 3, that's 64. Let's move that constant to the outside, so that's going to be 64 over 3. Now the integral of 0 to pi. Now sine cubed theta d theta. So this is going to be our new function. Now the problem with this is, obviously you may have said, well, how do we integrate this? I don't think we have seen this before, but there's a really simple trick that you can perform for all powers of sine and cosine, and it is the following. Remember the identity sine squared theta plus cosine theta equals to 1. So what we're going to do is we're going to rewrite this integral as 64/3 from 0 to pi of sine squared theta times sine theta. This is pretty much the same, but that means that we can now substitute for the following expression. Zero pi, and now we're going to have 1 minus cosine square theta times sine theta d theta. And the reason we did this substitution is because now we have a relationship between these two. We know that cosine theta basically integrates or differentiates into sine theta. So we can make the following substitution. Let's have u equals to cosine theta, and then we're going to have du equals to minus sine theta d theta, which is this term here. So this allows us to write the integral in the following form. So we're going to have to add that minus on the outside to balance this out here. So 64/3 of 1 minus u squared du. So now we have simplified this problem, and all we need to do is we need to integrate this with respect to u. So that's going to be u minus u cubed over 3. So if we replace the value of u back in here, so that's going to be cosine theta minus cosine cubed theta over 3 from 0 to pi. And now once we evaluate this, we're going to get the following. So I don't think it fits here. I'm just going to write it down here at the bottom. So in the end, the value of our integral is going to be 256 over 9. So that's going to be the value of our integral. So in this video, we just explore something really interesting, and it is for general regions, circular regions that do not lie on the origin. How do we deal with them? Well, to find the limits of r, we need to perform this kind of thing. We substitute for the values of x and y by r and theta into the equation of the circle, given the origin, the new center. And then by finding the roots of this quadratic equation on the radius, we actually find the limits of r. So this is a really important concept. And remember that polar coordinates extend to more than just circles. We could have a lot of other shapes, just to show you an example of what we can have with polar coordinates. There are things called polar graphs, which are not usually covered in most standard calculus courses, but I might make a video series on it because I think they're really interesting and they're really nice to draw. So there are polar graphs, which are essentially graphs that are drawn in terms of parametric curves. So parametric curves basically r and theta. So we can have x and y here. And then basically we're going to have shapes that this is called a cardioid, which looks like a little bit of a fat heart. If you flip it upside down, it looks like a heart. And it's called a cardioid. So basically, there are shapes like this which might be expressed, the parametric curve which might be expressed in this case as a plus b cosine theta. So obviously in that case, when we're setting the limits of integration for r, what we would do is we would have r go from 0 to that parametric form, a plus b cosine theta, because that curve sets the limit or the boundary for r. So that's how we would go about it. And then for theta, we would just use the same logic. We would see how many quadrants does the curve cover, then that would go from 0 to 2 pi. So, and then you can have intersections of curves. So you may have an area that is between two polar graphs like that, and then obviously you would need to adjust the limits accordingly. So it can get fairly complicated, but this is just a topic that I might cover in a future series because it requires a lot of knowledge about how to draw polar graphs and so on. But hopefully these 3 videos have shown you some of the applications of polar coordinates and polar using them to solve double integrals. And in the next video, I'm going to be talking about how to extend some of the application of double integrals to find the volume between two surfaces.